Good morning, SUPA. Another wonderful day of molecular geometry notes. Right? So today we're going to deal with something called hybridization. So let's go ahead and get started. So we know that a covalent bond forms when orbitals of two atoms overlap. Okay, so we're bonding, we're making these covalent bonds, and we've talked a little bit about this. Our orbitals overlap. This overlap is occupied by a pair of electrons having a high probability of being located between the nuclei of the two atoms. And by the way, this pair, okay, they must have opposite spin. Okay, just like we were filling in our orbitals, these guys have opposite spin also. All right. So something I want to stress, or this is what we're really kind of talking about, are valence atomic orbitals in a molecule are different from isolated atoms. So let me see if I can visualize this for you. So if we look at, let's say we look at fluorine, okay, and fluorine, its electron configuration is 1s2, 2s2, 2p5. Right, so if we were to focus on this the p orbital, right, so our valence electrons would have an up, 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 down, down, okay, and that would have this empty p. Right, now, what's the shape of this p orbital when this is by itself? Well, the pz, this pz orbital, would have the structure of that dumbbell. Okay, this is what that pz orbital would look like if fluorine is by itself. Now, we know that when we make diatomic fluorine, when these actually make the molecule, we know that this pz, these two pz orbitals overlap. So we get something like this. Okay, and the shared electrons are in here. Okay, so this is one fluorine atom, and this is the other fluorine atom. So once we start overlapping, the orbitals change. Okay? The orbitals change. Come on. So when we start orbital mixing, or orbital mixing, is called hybridization. These new orbitals are called hybrid orbitals or degenerate orbitals. These hybrid orbitals or these degenerate orbitals are orbitals, all the orbitals are equal in energy. Number 4. There are 3 common types of hybridization. SP, SP2, and SP3. There actually used to be more. We thought there were 5. Turns out that the model that we used to use, the 2 extra hybridizations, don't work anymore. And we'll talk about that in a second at the end, but we're going to focus on these 3 different types of hybridization. The spatial orientation of each type corresponds with the arrangement of electrons predicted by VSEPR. Okay. So these hybrid orbitals are actually work with VSEPR, okay? And if we didn't have these, VSEPR wouldn't work. Now, what atoms actually do this hybridization thing? So hybridization can occur when the following are central atoms. So these are central atoms. Beryllium, boron, carbon, nitrogen, oxygen, silicon, phosphorus, sulfur, arsenic, selenium, iodine, bromine, and xenon. Okay, so these are the ones that do this hybridization. In reality, we probably won't ever see any of these. Okay, we'll probably focus mostly, we're really going to focus mostly on these guys. All right. But once we know these guys, silicon, phosphor, and sulfur, okay, remember Okay, these guys silicon acts like carbon, phosphorus acts like nitrogen, sulfur acts like oxygen. So once we know these guys, we know these ones. And then these ones, we probably really won't see much of, right? Okay, so that's what we're going to focus on. Now, what is this hybridization stuff? Well, what I want to do is I want to look at carbon. Okay, so if we look at the element carbon, its not diagram is this. It's got 4 valence electrons. And if we draw, okay, it would be 1s2, 2s2, 2p2. So this would be our 2s, 2px, 2py, 2pz. We have an up, down, and an up, up. Now, if we're just to look at this, how many bonds does it look like carbon wants to make? Well, it looks like there's only 2 electrons that it wants to share, okay? So it looks like it only wants to make 2 bonds. But how many bonds do we know carbon makes? We know carbon wants to make 4 bonds. But why? It only has these 2 unpaired electrons. Well, it turns out that carbon mixes or hybridizes its orbitals. So we know that carbon really acts like this. And what happens, it takes the 2s and the 2px and 2py orbitals and 2ps, 2p and 2pz orbitals and combines them into 4 equal orbitals called sp3 orbitals. So we know if we have carbon by itself, we know we have 2 electrons here, and we have 1 in the px and 1 in the py. Well, when this bonds, now remember, this is during bonding, okay, it doesn't act like this. What happens is it takes this s, this is px, py, pz, and it mixes them all together to give us 4 orbitals. And they're called an sp3, 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 sp3. Now, it still has these 4 valence electrons, but instead of up, down, up, up, now we would have up, 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 which corresponds to that. And now carbon wants to make 4 bonds. So this is what hybridization is all about. It gives us this reason about why this is happening. Okay? So now what we're going to do is we're going to go through these 3 main types of hybridization. So let's start with SP hybridization. And a perfect example where SP hybridization occurs is in BeF2. Right? So in this case, beryllium is our central atom. And if we draw its knot diagram, it looks like that. Now, does it look like beryllium wants to actually make any bonds? Well, if we look at its electron configuration, 2s, 2px, 2py, 2pz. It doesn't even look like it wants to make bonds. It's happy. It has an electron. It's very happy. Okay. So it doesn't even look like it wants to make bonds. But it does. It will make two bonds. The question is, how does it do it? Well, what happens is it mixes two orbitals. Okay, now remember, this generally has a little bit less energy than the p orbitals, but not much. So what happens is beryllium, when it bonds, mixes these two orbitals. So instead of having a 2s, a 2px, a 2py, and a 2pz, okay, these two, the s and the p orbital mix, and we get something called an sp, an sp, and then we still have 2py and 2pz up here. And one of these electrons is here, and one of them is here. So now, these two orbitals, these sp orbitals, have equal energy. And now we can see why beryllium wants to make two bonds. So let's write this. The s and 1p orbital reorganize to produce two equal sp orbitals. Now look at, if you however many orbitals you take, you get the same amount of hybrid orbitals. So I took one s and I took one p. So I took an s orbital and a p orbital. That's two. If I have two to start with, I have two to end with. Okay, that's the rule. Okay, if I used 3, I would have 3 down here. If I used 4, I would have 4 down here. Now, how many domains of bonding are there going to be around this beryllium? Well, if we look at beryllium now, it's going to do this, or beryllium fluoride. So what's happening is we're forming a sigma bond. This is a sigma bond. And we are overlapping the pz orbital, the 2pz orbital from fluorine, and an sp hybrid orbital from beryllium. Okay, and that's where they're going to be sharing these two electrons. Right? And the same thing would happen on this side. Now, how many domains do we have around this beryllium atom? Well, if we use VSEPR, Oops. There are two domains. Both of them are bonding, which means this guy is going to be linear. When we have SP hybridization, these are usually linear molecules. Okay, so that's when we're mixing an S and one P. Let's look at our next type, and this is sp2 hybridization. Now, if we look at this name, it tells us what orbitals we're mixing. So we're taking an s orbital, and we're taking 2 of the p orbitals this time. Okay. So this tells us, let's write 1. We are mixing an s orbital and 2 p orbitals. So now, how many orbitals are we mixing? So we're taking 3 orbitals, we're mixing them, and we're going to get 3 equal sp2 orbitals. So if we mix 3, we get 3. So this gives 3 domains around the central atom. And if you look at VSEPR, okay, it usually gives us trigonal planar molecules. So let's try one. Right, so let's look at BF3. So boron is our central atom. Now, if we look at boron, it's in group 13. How many bonds does it look like boron's going to make? Well, it looks like it's only going to make 1 bond, but it will actually make 3. All right, it will make 3. So if we look at its electron configuration for boron, we have 2s2. We have an up-down and an up. And what's going to happen is we're going to take 3 orbitals. We're going to take this S, this P, and this P, and we're going to hybridize them. We're going to mix them. Okay, so these reorganize. Or they mix. And we end up having 3 equal sp2 orbitals. Now, we didn't mix this guy, so he's still here, and he has a little bit more energy than these guys. So he would be up here. spz would still be up here. Right, so we mixed 3 orbitals. We got 3 equal hybrid orbitals. Now, what would these electrons be doing? We would have up, up, up. Now we can see that boron is going to make 3 bonds. And that's going to give us that trigonal planar shape. Now, what orbitals, if we look at this bond specifically, what orbitals are overlapping? Okay, so the electrons here are being shared between an sp2 and a 2pz. Okay, so this would be from fluorine. This would be from my boron. So the sp2 orbital would overlap with the fluorine 2pz orbital, and this would again give us a sigma bond. All right. Let's look at sp3 hybridization, which we actually already just did. We did this to start with, because this is what carbon does. So just by looking at the name, we're going to take an S and 3 p orbitals and mix them all together. So we're taking 4 orbitals, so we're going to produce 4 degenerate or hybrid orbitals. Okay, so it takes an S and the 3p orbitals and makes them into 4 equal sp3 orbitals. So this is going to give us 4 domains around the central atom. And we're going to go right to CH4 again. Okay, so we know that CH4 does this. Again, the question is why carbon does this. Well, carbon, 2s, 2px, 2py, 2pz. And we got an up-down and an up-up. Okay, so now this time, when carbon bonds, now this is when it bonds and is a central atom. If it's by itself, this is what we see. If it bonds in a molecule, it's going to reorganize these. It's going to take all of these orbitals, and he's going to mix them, or reorganize them, or hybridize them. Right? So instead of having an S, a P, a Y, and a Z, these mix, and we get 4 equal orbitals, called sp3 orbitals. And now, these can share with the hydrogens. Now, what shape do we usually get with carbon? We usually get that tetrahedral shape, right? Because we have 4 domains. We have 4 domains. 1, 2, 3, 4. Now, what's overlapping? If we look at this bond between carbon and hydrogen, what's overlapping? Okay, so we have 2 electrons here overlapping. The carbon end is an sp3. The hydrogen end is just a 1s. Okay, and they're overlapping. end to end. So again, this is a sigma bond. Now, oxygen and nitrogen actually do the same thing, and I want to go through them. So if we look at oxygen, okay, it wants to make two bonds. It wants to make two bonds. So you'd think it would just go here and here. Okay, so like for H2O. But if it just did that, okay, if it just bonded here and bonded here, we would probably really just get a bond angle of 90 degrees. And that's not what we get. Okay, this doesn't happen. Okay, we know that it doesn't. So something else has to be happening here. So when we look at oxygen, okay, it's got 2s, 2px, 2py, and 2pz. And it's got an up, down, up, 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 down. Okay, so this is what oxygen is when it's not a central atom, when it's by itself. What we find is this is going to go through sp3 hybridization. So it's going to mix all three of these orbitals. It mixes them. And we end up with 4 sp3, orbitals. And we have 1, 2, 3, 4, 5, 6 electrons still in here. So we would go 1, 2, 3, 4, 5, 6. Okay. So now we have 4 domains. These are the 2 that it's going to make bonds in. And again, it's probably going to make sigma bonds, especially if it's order. All right. Now, why do we think this? Well, if we look at oxygen when it's bonded, it actually kind of makes a tetrahedral shape. Okay, it makes a tetrahedral shape. So we know, like in water, we have that. But there are 2 extra domains. There's this sp3 and this sp3. So coming up, there are 2 electrons, and coming out, there are 2 electrons. So we end up getting this tetrahedral shape, which is really telling us, look, we must have this mixing going on to get this shape. That's why we think this is happening. Now, nitrogen does the same thing. If we look at NH3, it again kind of makes that tetrahedral shape. We have an H, and an H, and an H, and then up here, we have these 2 electrons. So we again have this tetrahedral shape. And to get that tetrahedral shape, we think that there's, again, some hybridization going on. So normally, nitrogen is this. Oh, this is a 2s, 2px, 2py, 2pz, up, down, up, 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 and that's it. Now, these in nitrogen are again going to hybridize. Okay, so these mix, and we end up with sp3, 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 sp3. 1, 2, 3, 4, 5. And again, now we have these three equal orbitals where we're going to make our bonds. Okay. And again, this produces our 4 domains, which generally give us that tetrahedral shape. Okay, now this isn't a tetrahedral shape because, all right, there's nothing here. It's this pyramidal shape, right? But that's what's happening with the bonding and the hybridization. Okay. So silicon is going to act like carbon, so it's going to do sp3 hybridization. Okay, just like this. It's got the same. Okay, it's got the same configuration except it's in the 3s instead of the 2s. Phosphorus will act like nitrogen. It'll do the same sort of thing with nitrogen. And sulfur will do the same thing as oxygen because they're all in the same group. They have the same valence electrons. They do really similar things. Now, I want to quickly spend a little bit of time with what are called hypervalent compounds, and we know what those are. And these are hypervalent compounds, or compounds that exceed the octet rule. Now, we used to think that these compounds produce 2 more types of hybridization. Okay, so we used to believe that S, P, and D orbitals would hybridize. So for example, phosphorus, we thought, well, we know that phosphorus is this, 3s, 3px, 3py, 3pz, and then we have our 3ds. And this would be up, down, up, up, up. Phosphorus will expand its octet. It can have more than 8. And what we used to think is we thought that these would hybridize with a D. All of these orbitals would mix. And these would be called sp3d hybrid orbitals. And we would get, well, we're mixing 1, 2, 3, 4, 5 orbitals, so we would get 5 of these. And then there would be these 4 3Ds left. We would get up, 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 which means now we can have 1, 2, 4, 6, 8, 10 electrons around phosphorus. Well, it turns out that this isn't true. It doesn't happen. So experimentation has shown that d orbitals have substantially higher energy than the 3s and 3p orbitals, and will never hybridize. Okay. It won't happen. So these d orbitals have a lot more energy than these guys. Okay. So remember, matter of fact, okay, we're going to, before we put anything in a 3D, we put them in the 4s first. Okay, so the 4s actually has less energy than a 3D. So these guys have a lot more energy than these. So it turns out that this hybridization won't happen. So what does happen? Well, I'll be honest. That's a good question. We don't know what happens. We don't know why these hypervalents happen. So we don't know why these hypervalent compounds occur. All right, now, you do not need, okay, we'll never use this hybridization. Okay, so this is something right here, okay, that chemists are still working on. Okay, so this is a big area of research on why this hypervalent stuff happens and why isn't there hybridization and how is this bombing occurring, all right? Why do we get these expanded octets? Okay, so you don't have to be able to deal with hypervalence. So if you ever see sp3d hybridization or even sp3d2 hybridization, you don't need to know those, okay? Don't need to know them. All right. That's where we're going to end for today. All right. Have a good afternoon, and we will see you next time.